Well, good afternoon, everyone, and thanks for coming to the presentation this afternoon. I'm going to try to get or keep us on schedule, and let me go forward into the denser part of my presentation. I have been struggling to take this somewhat lengthy and complicated topic and make a good introduction to it, and that's what I'll work on here today. This information's going to be, there's another version available on a webcast, and we'll have an application note on this to get to it to more detail. But I think I can give you a good summary of the issues with respect to finding the signals that you're trying to find, especially if those signals are hard to find. And that's especially important these days because we're dealing with much more dense spectral environments and more agile signals. And what that means in a lot of cases is that a very crowded spectrum means that if your product has some sins, they will often be noticed. Or that you may be dealing with sins from someone else's product or emission. And some of these areas here, let's talk directly more about the measurements themselves. The idea is to get a better understanding of the way of how short of events we can intercept, the probability of intercept, or how to trade off various factors that affect that. And that includes, do you detect the signals? How accurately can you measure them? What sort of power and frequency resolution you get? And can you detect every event? Your individual situations are likely to be different, so I'll give you a general insight into the most important factors for that here today, and then you can take that to make better measurements later. You're probably familiar with swept spectrum analyzers. The problem is, when you are sweeping at one frequency, when your resolution bandwidth is at one frequency, you're missing something at other frequencies. So fixed LO schemes where you digitize a certain bandwidth are the ways to get a well-defined probability of intercept. These are typically in things like vector signal analyzers or in FFT analyzers, where we're not using a swept LO. It's sometimes called a basic mode, but what it really means is that the digitizer is not a baseband digitizer, it's an IF digitizer. So instead of producing baseband samples like an oscilloscope, it produces IQ samples with some implied LO frequency. So that's the IQ mode. That's the way typically these FFT and vector signal analyzers are doing their sampling. Same thing with real-time analyzers. So with real-time analyzers, I did some discussion of this in a paper yesterday morning. For here, I'll just note that the real-time analyzers do use this fixed IF capability, this fixed IF digitizing, but they have a high-speed dedicated FFT processor. Relatively inflexible processor, but very high speed, hundreds of thousands of FFTs per second, which gives you consistent measurement speed and improves your chance of detecting the signals you're looking for. And that does lead in some cases to specialized displays. We won't really talk about those much today. Let's see, and by the way, these are spectrum measurements where we're talking about probability of intercept in most cases. They are scalar measurements, that is magnitude versus frequency. They're not vector measurements of time domain or demodulation, but those can be done with the same hardware. I'll talk about that at the end of the presentation. There are two things here, though, that really give the core insights in terms of probability of intercept and what's going on with FFT analyzers. And that is, typically we've got a stream of samples coming past, and we're taking a block of these, 1024, 512, it's typically powers of 2, sometimes it can be hundreds of thousands, but we're taking a block of these samples, doing an FFT, and creating a spectrum. And then, if we can do the calculations fast enough, then what that means is we take another block of samples or another FFT even before the first FFT is done, even before a new time record. So this is overlap processing, meaning each new FFT is done so fast that it can be done before a new set of samples is done. So you take some of the samples, the last samples from the previous FFT, and a new set of samples for the new FFT. But the other thing that goes on in almost all FFT processing is some sort of windowing. Let me back up. The problem with an FFT is that you don't get good results if the signal that you're measuring is not periodic in the window. And of course, typically, signals aren't periodic in your particular window. I'll show some examples of that as it comes up here. With respect to POI and how it intersects with these issues of windows and sampling and overlap, we have a couple of possible goals, sometimes a trade-off between those. One of them is, are you trying to make sure you never miss a signal, getting it 100% of the time? Or are you particularly interested in an accurate amplitude reading? And those are essentially competing goals. What's often happening if you're dealing with optimizing probability of intercept is you're operating at the outer envelope of measurement possibilities. If you improve one thing, say you improve your power measurement accuracy, it will cost you elsewhere. You might not have as good a probability of catching the signal. On the other hand, if you want the maximum probability of capturing a signal, you may have to give up some in terms of the accuracy of the measurement, at least in a normal real-time analyzer mode. So where that comes from has to do with the windowing I mentioned a minute ago. If you do an FFT of some time samples, and if that signal is periodic in your time record, you get very good resolution, very good accuracy. But if the signal is not periodic in the time record, you don't have an even number of cycles of your signal in the time record, if you move this off, you start to see much poorer signal-to-noise ratio, and you start to see wider resolution bandwidths. That's an effect of non-periodicity of the signal in the time record. And that's why in most cases you do weight the signal in the time record by some sort of window, meaning you maximum weight the signal at the center of the window, and at the beginning and the end of the time record, you downweight the signal. You attenuate the signal. What that does then, it trades two things off. It gives you good dynamic range as opposed to these signals here, but it widens your resolution bandwidth. So you're trading away resolution bandwidth or resolution for better dynamic range and for better amplitude accuracy. That's one of the trade-offs that's going on here. We're talking about a situation where any one thing will trade off against others. That's shown here in a little bit different way. In this case, here is a rectangular window, which is to say no window. We're weighting all the data, all the samples in the time record the same, and if we move the signal around, we notice the amplitude changes, the apparent bandwidth of the signal changes, and that way we get a very good result only if the signal is periodic in the window. On the other hand, if we use other windows, which trade off some of that resolution bandwidth, we get better amplitude accuracy, we get better dynamic range, but we get poorer frequency resolution. Some of the windows you'll hear about, this is in FFT analyzers, things like Kaiser or Blackman-Harris or Hanning or Hamming or rectangular or uniform or Gaussian. Those are all different shapes of weighting, but the rectangular or uniform window is essentially no window, no weighting at all. That gives you the maximum resolution, but it hurts you in terms of dynamic range and accuracy unless your signal is on bin or periodic in the time record. The other thing that happens, so here for example is in a shape of one window of one FFT. These are the samples we're using, and here's the next FFT with some overlap between the two FFTs. Overlap in time. That way some samples are FFT'd in both FFTs. If the signal is only on for much less than one window or one time record length, then we don't get accurate amplitude. We can detect this signal, but unfortunately it only occupies part of the time record, so the amplitude doesn't look correct. So this is one of the trade-offs I mentioned earlier on. We can detect that the signal exists reliably, but we don't get a good accurate amplitude measurement of it. And that can be viewed as essentially the area under the curve. That's one way to see what that amplitude derating would be. Another way to look at that is that the position of the burst, once again we're talking about a signal that is shorter than the time record, two different signals here, the red one and the blue one. Both of them are the same length, but they occurred at different times in the time record, and we've got that window that we saw before. A signal that occurs in the center of the time record will have a higher apparent power. That same signal occurring at the beginning or the end of the time record will be windowed off, and so the amplitude accuracy will be much poorer. And that's shown here. The difference in this case, just by changing that location, is about 25 dB. So again, we could detect both of these, but we wouldn't get as good of an amplitude accuracy depending on where this signal occurred in the window. And in many cases, unless you're making a triggered measurement, you don't get to choose where it occurs in the window. Although that's one of the bits of wisdom I will offer. If you're trying to get high probability of intercept, then in things like the vector signal analyzers, using a magnitude trigger, which evaluates the signal magnitude on every single sample and synchronously triggers those, can ensure that you have the signal where you want it in the window. Plus, you can use things like gated sweep. I'll come back to that at the end of the presentation. Another issue with this then is sampling rate. If you're trying to get high probability of intercept over a really wide bandwidth, you're sampling very quickly, short time records, it's harder, with very little overlap, it's harder to get 100% probability of intercept. If you're analyzing over a narrower frequency span, then once again this is an information theory challenge. Analyzing over a narrower frequency span means the samples come slower, but you're FFTing fast at the same rate, so you have more overlap and more chance of getting the signals. So if you are trying to get 100% probability of intercept, don't set your span any wider than you absolutely need it. The narrower the span, the higher the probability of intercept will be, because you're overlapping these FFTs more and more extensively. But another issue that comes up then is if you want maximum amplitude accuracy. So your probability of intercept means the probability that you're going to get 100% amplitude accuracy. Then you can change window size and change how much, you can trade off some of the resolution by going for a shorter window and wider resolution bandwidth for higher accuracy. So you can make a 100% accurate measurement, the same accuracy for a transient signal as you would with a continuous signal, using a narrower in window time or wider resolution, and get full amplitude accuracy. So once again, we loop back to that issue of you're operating at the maximum information envelope. If you want something more in one area, you're going to want to trade something else and trade something off in the other. And that's actually always a good practice in engineering of these systems, is to understand what it is that you want the most. Is it just to detect the signal? Is it to get 100% accuracy? Is your signal just one signal, or is it a repeating signal? Is it all right if you just capture one once in a while, that you don't capture every one, but you capture one of them occasionally with perfect accuracy? The other thing that interacts with this is detection with the real-time analyzers or the vector signal analyzers in a frequency mass trigger mode. Because in some cases, what you're looking for may not happen every second or every minute or every hour or every day, so you may want to use something like a frequency mass trigger function. And the same issues come into play. With overlap, we can determine how long the signal has to be and how big it has to be. If the signal is very near the noise level, then the signal will have to be longer in its duration before you can detect it. If the signal is way, way above the noise level, you can detect it over a much shorter interval because it stands out from the noise. Its power is much different than the noise. Its frequency behavior is much different than the noise. So in this case, we chose a 40 dB figure just as an example. And if we take what part of this signal occupies either of these windows, in this case the worst place to be is where both windows are intersecting and there's minimal overlap, then the window shape actually determines whether we need 11 samples or 65 samples to see that signal with accuracy, or to detect that signal 40 dB above. So I don't really have the time today to go into all of the trade-offs back and forth, but I did want to give you an idea. If you have signals that are shorter, they're harder to detect. If you have signals that are closer to noise, they're harder to detect. If you have signals that happen very rarely or only once, they're harder to detect. Now, if the opposite of those things is true, then you can detect them more easily. You can detect them with better amplitude accuracy. Just keep in mind that we've moved out of the swept spectrum world where you could trade some things off without a problem, and we're now in a sort of an information theory limited world where if you're trying to find things that are very elusive or very rare, use all the tools at your disposal. Recognize if you want maximum accuracy, you're going to need something longer, or you're going to need better signal to noise. I mentioned earlier on about using narrower spans. Again, one of the other trade-offs is if you can sample slower and do more overlap, meaning you sample slower at a narrower bandwidth, but you're FFTing just as fast as before with this fast FFT hardware, then that means you can get more overlap and you can improve your probability of intercept. You can find signals closer to the noise. If you trade off any one of these, you'll get benefits in the others. So in this case, for example, going from 200 megahertz to 100 megahertz, for the Blackman-Harris window, we needed 65 samples before. Now we can use only 8 samples and detect this signal at the same level above the noise. So these are not all linear relationships, but you can find the ones that are most favorable to you. So in this case, for example, it takes twice as long to get the samples, but they're 8 times better in terms of detecting the signal. 8 times shorter signal, we can detect it with the same probability. I won't talk about the real-time analyzers and the displays. The other thing, because I think you've seen that kind of material before, the other thing I wanted to mention then is that if you're dealing with these transient or very difficult to detect signals, the other technique that works really well is to use the same sort of hardware, perhaps use a frequency mass trigger or a magnitude trigger to trigger on the signal, but then use the vector signal analysis software. The reason for that is that you can grab a large chunk of the data in real time, that is gap-free, and post-process it. And by post-process it, you can take the same data and look at it again and again and again with a nearly infinite amount of overlap, even sample by sample overlap, the equivalent of billions of FFTs per second. You can change the windows and change the window shape and change the window size and use things like gating and trade all of these things off one measurement after another to optimize for different uses. So remember when I said earlier that the problem was that anytime you tried to make one thing better, it cost you in some other aspect. Accuracy versus dynamic range versus probability of intercept versus resolution bandwidth. If you want all of those things, then the VSA software, by capturing the signal and then allowing you to reprocess it and reprocess it and reprocess it, just changing the settings, allows you to make successive measurements, each one of which is better optimized for the things you want to see. So by 3 different measurements, you might be able to optimize 3 different parameters that way. Plus, you can do it all visibly. You have the signal. You've captured it all over whatever bandwidth. You can change that bandwidth. You can change the center frequency you're at and look in at specific signals, among others. So that's sort of, often in engineering, if you find yourself operating at the edge of the envelope, you're sort of looking for a trick or a way out or a special approach. And what I would say in this case, the best bet that way is probably VSA software, time capture, whether you're triggering on the signal or just capture a big wad of time and then find the signal you want, and then reanalyze over and over and over again. The other advantage that has, I think that we've all experienced, is you go to make a measurement on a transient or repeating signal, you make a measurement, then you switch the analyzer's settings around a little bit and you make another measurement and you get a different answer. And you're not sure, well, did the signal change, or was that a result of the parameter change I made, or is there some evil interaction going on there? If you've got a time capture, then you've got the same data over and over and over again. You can make all the changes you want, and you know that all the changes you see in measurement results are due to the change in the setting, not the change in the signal, because you got the same signal over and over and over again. And of course, if the signal only happens every minute or every hour, then that allows you to grab it and keep it and send it to someone else for analysis. So that's sort of the overview I wanted to give you today. We're coming out with a new paper and an app note on probability of intercept that goes through this in more detail and gives you the numbers and equations you need if you need to actually quantify that. What I would say is if you're generally interested in probability of intercept and you want to improve that, then things like real-time analysis, frequency mass triggers, those can allow you to spot the things and then capture the signal and do that reprocessing. That'll allow you to get the maximum available in a particular signal. So I'm sorry to go through this so fast. I hope I gave you at least some good guidance and directions to go to make more productive measurements that way. I will be at the Agilent booth after this. Be happy to talk with you at all, or I can give you a business card and we can talk offline. And thanks very much for coming today.